I think we can start.
Shall I start?
We'll have kind of 1 minute, right?
Yeah, okay.
So we'll start at 7. Yeah, now it's 7. Okay, so maybe we can start. Okay, good evening, everyone. So Professor Vamsi Pingali will continue his talk on Calabi's conjecture. Over to you, Vamsi.
Okay, thanks, Diganta. Okay, again, this talk will also be very awkwardly paced. I sincerely apologize for that. So last time we looked at why to care about complex manifolds. I gave you a laundry list of reasons. I also told you why you need to care about Calabi's conjectures, well, whatever they are. Then we defined complex manifolds, holomorphic functions, discussed some subtleties of several complex variables. We saw that it's actually not trivial to come up. Yeah.
Vamsi, sorry to interrupt. Would it be possible to make it full screen?
So that's the thing. This particular app. Okay, let me do it this way. If I need to annotate, I'll come back to this.
I see. I got it. Now you can annotate. That's why you.
No, I need to use that app. That's why. Anyway, they can get types. Let's see.
Sure. Yeah. Okay.
So we saw that it was hard to come up with examples of compact complex manifolds, actually, as opposed to, say, real smooth manifolds. And nonetheless, we came up with examples by the quotient construction, namely tori, projective spaces CPN, and the Hopf surface, which is a quotient of C2 minus the origin. Then we saw that we could actually come up with lots of examples of submanifolds of projective spaces by taking a bunch of homogeneous polynomials, setting them to 0. And well, if you're lucky, such an object will be a submanifold. Yeah. Then we wanted to answer the question of when exactly a compact complex manifold is secretly a submanifold of projective space. To this end, we defined holomorphic line bundles and came up with a very canonical example, namely the O1.
Excuse me?
Yeah.
Is there voice repeating somewhere?
I think maybe someone, maybe you can mute yourself. Maybe if everyone can mute themselves. Yeah. Now I hope there's no problem, right? Yeah. Okay. All right. So yeah, we looked at line bundles. In particular, we looked at the O1 line bundle over projective space, and we looked at Hermitian metrics, that is smoothly varying inner products, the Chern connection, curvature, and what it means for curvature to be positive. So that's what we did the last time. So let's continue. So here's a question. When is a 2n real dimensional manifold secretly an n complex dimensional manifold? Yeah. Forget for manifolds. What about for vector spaces? If I give you a 2n dimensional vector space, say R2n, how can I think of it as Cn? Yeah. So what do we need to know? We need to know precisely what it means for square root of -1 to act on vectors in this vector space. Yeah, that's what we really need to know. So we define an almost complex structure to be simply an endomorphism of a vector space to itself, so that j square is -I. The most obvious example is the one that makes R2 into C. It simply takes 1 and produces 1 times I is I and I square is -1, right? That's what this does. So in general, you can prove that whenever there is an almost complex structure, V is even dimensional. Well, that's trivial. Just take the determinant on both sides. And more importantly, there's always a basis so that J is indeed the standard almost complex structure, making R2n into Cn in the most obvious way. An almost complex manifold is a manifold such that every tangent space has an almost complex structure, and these almost complex structures vary smoothly. Yeah. Now, complex manifolds have an obvious almost complex structure, namely you choose a complex coordinate chart So the tangent space is holomorphic tangent space is Cn, and Cn can be identified with R2n, and the most obvious almost complex structure, namely this particular one, does the job. Yeah. Unfortunately, if you give me any almost complex structure, almost complex manifold, it need not be a genuine complex manifold. In other words, you need not be able to find coordinates x and y, so that in the d by dxi and d by dyi basis, this almost complex structure is standard. That may not always be possible. And this happens if and only if something happens. That's the Nylander-Nirenberg theorem. We don't really need that. Just mention it anyway. All right. Sorry, let me just keep track of time. Yeah. Okay. Okay. So what's our aim? We need to do differential geometry. So we need to talk about distances, lengths, and angles. So we consider the complexification of the tangent bundle of M. What does that mean? M is a complex manifold. So you can think of it as a 2n dimensional real manifold. So it has a tangent bundle, that is the collection of all tangent spaces given a structure. Now, each of these tangent spaces is a real vector space of dimension 2n. You can tensor it with C to get a complex vector space isomorphic to C2n, right? So you get a complex vector bundle, which I'll denote this way. Now, if you take C2n, this J here, this almost complex structure, extends as a linear endomorphism. All I'm saying is, if you have any J from V to V, if you take V tensor C here and V tensor C here, you can extend J as a complex linear map from V tensor C to V tensor C, still satisfying this, right? Now, when you do this, this thing at each point decomposes into two complex vector spaces, the plus and minus square root of -1 eigenspaces. And indeed, the plus square root of -1 eigenspace turns out to be T10, the T10 we defined much earlier, the last time. And minus I turns out to be T01. Likewise, if you take the dual of the tangent bundle, the bundle of one forms, you get omega10 and omega01. More generally, if you take their wedge products, you get, as we did the last time, PQ forms. Some more linear algebra. Turns out, if you take the real tangent bundle and the holomorphic tangent bundle, if you're getting confused with all these things, just pretend you have R2n with the almost complex structure J, making R2n into Cn, or even simply R2 into C. This one is basically a subspace of C2, right? And these two are isomorphic, and the isomorphism is given very explicitly like this. Okay. So in other words, invariantly, it's V goes to V minus IJV over 2. I leave this as an exercise for you to check that indeed this beast is in the plus square root of -1 eigenspace of J. Okay. So notice that the usual metric on R2, the Euclidean metric, is preserved by this standard almost complex structure. What do I mean by that? What I mean is, if you take this one, right, this map actually preserves inner products. Why? What does it do? It takes the x-axis and rotates it by 90 degrees to give you the y-axis anti-clockwise, takes the y-axis, rotates it by 90 to give you minus x, right? And rotations preserve the inner product, preserve the metric, right? Okay, so bearing this in mind, there's a standard Hermitian metric on the holomorphic tangent bundle of the simplest possible complex manifold, C itself. And you can write it as dz tensor dz bar. And if you write dz as dx plus I dy and dz bar as dx minus I dy, it turns out, if you expand it out, you'll get the Euclidean metric plus this beast, okay? So in other words, the real part of a Hermitian metric that is preserved by J is a Riemannian metric. The imaginary part is a 2 form. It's a 1-1 form, okay, namely this form omega. Okay. So that's the bottom line here. And this 1-1 form omega can be defined invariantly without using coordinates, as it acts on 2 vectors and produces g of jx comma y. In other words, if you give me 2 pieces of information, a Riemannian metric that is preserved by the almost complex structure J, I can produce a 1-1 form out of it. Alternatively, if you give me a 1-1 form and J, I can produce G. If you give me G and omega, I can produce J. Okay, so any 2 of these can be used to produce the third one. So yeah, this is what this is saying. More generally, given any compatible Riemannian metric, namely a metric where J is like a rotation, it preserves the inner product, then this construction gives you a 2 form, and it's a 1-1 form, in fact. And using this 1-1 form, you can produce a Hermitian metric on the holomorphic tangent bundle. The bottom line here is, if you give me a compatible Riemannian metric, I can produce a Hermitian metric on the holomorphic tangent bundle and vice versa. Okay. Right. By the way, there are I'm not going to be very consistent in my choice of convention here. You see, there's a 2 here. I'll abuse notation, language, and everything you can think of, and get rid of the 2 whenever I feel like. Yeah. Okay. So now the first thing here is all complex manifolds are orientable. So for example, if you give me a non-orientable manifold, a Möbius strip, for instance, it can never be made into a complex manifold. And in fact, you can give the complex manifolds a very canonical orientation. You just choose a holomorphic coordinate chart, Z1, Z2, so on, and choose this basis vector. This orients each tangent space. Okay. And if you're familiar with another definition of orientability in terms of Jacobians being positive, please do this as an exercise to calculate the real Jacobian in terms of the complex one, and check that this actually makes it into an orientable manifold. So if you give me a compatible Riemannian metric, you can always talk about a volume form for an orientable real manifold. Namely, it is this particular expression locally. This volume form has a very nice formula in complex geometry. So when you choose coordinates where G and omega are standard at this point, you can show that this volume form is simply omega raised to n by n factorial. Okay, you can always choose such coordinates by just linear algebra. So the volume form of a compatible Riemannian metric on a complex manifold is simply omega raised to n by n factorial, where omega is the 2 form defined earlier. Now, if you give me a complex submanifold, the induced 2 form is simply the restriction of this 2 form.
Let me ask you a question.
Sorry?
Real vector field,
sorry?
Can be considered as a generator of a 1-parameter group of diffeomorphisms.
Consider what as a generator, sorry?
A real vector field.
Yes, you can, of course.
That is solving their differential equations.
Yeah, I mean, given a real vector field, you can, I mean, on a compact real manifold, sure.
Anyway, it may not be generated the whole thing local.
Yeah, okay.
Local
okay.
event.
Okay.
Similarly, can you do the complex vector field generates a complex?
Sure. If it's a holomorphic vector field, yes.
So, but what is the?
So if you take a
what differential equation you're solving?
So what is a holomorphic vector field after all? If you take a real vector field, I can say it is holomorphic if so if I take a real vector field, as you said, it generates a one parameter group of diffeomorphisms. If those diffeomorphisms preserve the complex structure, then you get a one parameter family of holomorphic diffeomorphisms, and this vector field is holomorphic. Or alternatively, if you give me a section of the complex T10, which is a holomorphic section, then you can take the real part of it, and that will give you a real holomorphic vector field whose one parameter family of diffeomorphisms are biholomorphisms.
It should be complex, say the compact complex manifold, the group generated by holomorphic vector field should be a complex Lie group, right?
Sure. That's right. I mean, I'm just saying that if you give me a holomorphic vector field, what would you think of as a holomorphic vector field? Locally, it is a holomorphic linear combination of the d by dz's, right? You would want to think of it like that. My point is, if you give me its real part, I can figure out its imaginary part too. So the point is, if you give me its real part, that gives you a real vector field. If you take the one parameter group of diffeomorphisms generated by that real vector field, all those diffeomorphisms are actually biholomorphisms. So that's the point. Or alternatively, if you want to do it more directly, you can, of course, you can solve complex differential equations, and you can do it that way also. But the cleanest way is simply this: take the real part and take the one parameter group of diffeomorphisms. Those will all be biholomorphisms. I
think it's good to relate the interpretation in terms of differential equations with the geometric way of thinking of.
No, I'm sorry. I don't. I'm unable to understand the question. As I said,
I'm not very clear about this, but the group generated by a real differential, real vector fields is a,
yes.
Say in certain circumstances, it will be a real Lie group.
Yes.
Similarly,
but if you take a specific kind of real vector field, real vector field satisfying certain differential equations, the resulting Lie group will be a complex Lie group. That's what I'm saying. And what differential equations must the real vector field satisfy? Those differential equations that ensure that it is the real part of a holomorphic vector field.
Hey, possible you can maybe think about it and write down what differential equation you're solving.
Those will be the analogs of the Cauchy-Riemann equations. But okay, anyway, I'll come back to it perhaps at the end of, maybe I'll just finish this thing. Okay, anyway, so the volume form of this complex submanifold is simply omega raised to s by s factorial, just second to this. Okay, so this is a comment, we don't need to bother about it. Okay, actually I do have some time, not a problem. Okay. Anyway, so as examples of compatible Riemannian metrics, so let's look at examples. The usual Euclidean metric on Cn, the usual thinking of Cn as simply R2n. You have the usual Euclidean metric. That is a compatible Riemannian metric because J in this case is simply a rotation. It preserves this metric. Likewise, if you take Cn quotiented out by a lattice, you get a torus, complex torus. The induced metric on it is also a compatible Riemannian metric. Okay. So the real question is, how do you come up with more examples of compatible Riemannian metrics in Cn? Yeah. So, and Kähler came up with this construction. What he did was, he took a smooth real function from Cn to R, a real valued smooth function, and took the complex Hessian del square phi by del zi del z bar j. So this gives you a Hermitian matrix, right? And if this Hermitian matrix is positive definite, it need not always be. But for example, if phi is equal to mod z square, then this will be a positive definite matrix, right? But it's not always one. And if it is one, then this gives you a Hermitian metric on Cn. Its real part gives you a compatible Riemannian metric on R2n. Okay. So this construction was originally due to Kähler, and so the metrics of this sort were called Kähler metrics. But now we call them by a different name. These functions, these smooth functions, satisfying this property that del square phi by del zi del z bar j is a positive definite matrix, they're called pluri-subharmonic. The problem is not every Hermitian metric in Cn is of this form. Unfortunately, given any matrix valued smooth function that is positive definite on Cn, you cannot always find a phi that does this. Okay. And indeed, why can you not do it? Suppose there is such a phi, such that h is del square phi by del zi del z bar j. If you take one more derivative, suppose you take del hij bar by del z k, then the right hand side will be del cube phi del z k del zi del z j bar. So you can interchange I and derivative with respect to I and k, and you can conclude that del by del z I of hkj bar is del by del z k of hij bar, right? So this gives you a non-trivial collection of equations that h ought to satisfy, without which you cannot hope to find such a phi, right? So not all Hermitian metrics are of this form. And the little calculation that I just did verbally can be stated in the following way, that if you take the induced 2 form omega given by hij bar dzi wedge dzj bar sum over I and j, that better be closed. Okay, so that's a necessary condition. In fact, it turns out due to some non-trivial applications of the del bar Poincare lemma, you can prove that this necessary condition is also sufficient. That is, every closed real 1-1 form on a ball is always of the form square root of -1 del bar phi for some real valued function phi. Okay, so this is called the local del bar lemma. So more generally, a Riemannian complex manifold Mg is said to be Kähler if this Riemannian metric is compatible with the complex structure, firstly, and secondly, the induced 2 form is declosed. So for example, metrics that you get using this construction are all by definition, not by definition, almost by definition, Kähler. Okay. Right. So Kähler manifolds are special kinds of complex manifolds with special kinds of Riemannian metrics. Unfortunately, not every complex manifold admits a Kähler metric. And the Hopf surface is a classic counterexample. If you take C2 minus the origin and quotient it out with Z identified with 2 raised to n times Z, it's diffeomorphic to S1 cross S3. And such beasts cannot be Kähler. So the Kähler condition is equivalent to finding local holomorphic coordinates, so that these 3 things are all standard up to z square. Okay, so what does that mean? Recall that in usual good old Riemannian geometry, you can always find smooth coordinates near every point, so that the metric is standard up to first order. In other words, the metric at that point is simply the identity matrix in the coordinate basis, and the derivatives of the coefficients of the metric, the first derivatives are all 0, right, at that point. The second derivatives need not be. In fact, the second derivatives tell you what the curvature is, right? So likewise, you can ask whether, given a compatible Riemannian metric on a complex manifold, you can always find holomorphic coordinates such that the metric is standard up to first order. That's not always true, unfortunately. And it is true precisely when this compatible Riemannian metric is scalar. In other words, omega is D closed. Okay. So how do you prove this? This is not rocket science. What you do is you take any old holomorphic coordinate chart, your favorite holomorphic coordinate chart, change it using a linear transformation so that the metric becomes, so that let's work with H, so that H at that point becomes the identity matrix. But the problem is the derivative of the coefficients of H, the first derivatives need not be 0. So the trick here is you further change your coordinates by adding a quadratic term. Okay, instead of just linear algebra, you just add a quadratic term and you choose the coefficients of the quadratic cleverly so that the first derivatives at that point become 0. Now, to be able to do it, it will turn out that you need the Kähler condition. In fact, you can do it as an exercise. The proof is in Griffiths and Harris, but nonetheless, so one direction is like that. If you give me the Kähler condition, you can find coordinates that do this job. If you find coordinates that do this job, the Kähler condition is trivially satisfied in these coordinates and hence in all coordinates. Yeah. The Kähler condition is also equivalent to the claim that the Levi-Civita connection of G, so this is a Riemannian manifold, so you have a Levi-Civita connection on the tangent bundle, on the smooth tangent bundle. Now, this is also a complex manifold. So you have the holomorphic tangent bundle T10, right? And T10, the holomorphic tangent bundle, I mean, if you're dealing with, say, Cn, then T10 is isomorphic at each point. The tangent space is simply Cn. Or it is also isomorphic to R2n, right? So on the R2n part, you have the Levi-Civita connection, roughly speaking. On the Cn part, you have the Chern connection. Okay. The point is, under the isomorphism that takes these two to one another, this particular isomorphism, right? Under this isomorphism, the Levi-Civita connection and the Chern connection ought to coincide. This the requirement that they both coincide is equivalent to saying that the metric is scalar. Okay. Right. So yeah, so that is so these three conditions for Kählerness are equivalent. So again, not every manifold admits a Kähler metric, but many do. In particular, any submanifold of projective space admits a Kähler metric, okay, as we'll see. Okay, so if you take the, recall that the de Rham cohomology consists of closed forms quotiented out by exact ones. Now it's finite dimensional for compact manifolds. Several ways to prove this. One way is to use Hodge theorem. I believe that some Hodge theory was covered prior to this lecture, so maybe I might be repeating certain things, but nonetheless, it's always good to see these things more than once. So all right, so the de Rham cohomology is finite dimensional for compact manifolds. Likewise, one can form the Dolbeault cohomology groups HPQM for complex manifolds. I think I might have done this the last time, but might as well use this annotation business at least once now that we've taken the trouble to do these things. So HPQM is simply del bar closed PQ forms quotiented out by del bar exact ones. That is, omega is equivalent to eta if omega is eta plus del bar of some gamma. Okay. And del bar omega and del bar eta are both closed. Okay, so this is the Dolbeault cohomology. So for Kähler manifolds, it turns out by Hodge theory, which I hope has been covered for you, is that you have this particular equality of these cohomology groups. So for example, if you take a K form, if you take any K form, you can write it as a sum of PQ forms such that P plus Q equals K, right? Now this thing holds true even for cohomology classes. If you have a Kähler manifold, the kth de Rham cohomology group is a direct sum of the PQth Dolbeault cohomology groups for P plus Q equals K, right? Well, how do you prove it? Well, Hodge theory, very quickly, what it says is that every cohomology class on a compact manifold has a very canonical representative satisfying a certain PDE. Now, it turns out the representative for this particular class is exactly the sum of the representatives of these things. I mean, if you take this representatives and you write down the PQ parts of these this representative, those will all satisfy that the desired PDE, and they will all be the canonical representatives for these classes. Okay, that's how this works. The Kähler condition is used to conclude that this thing, that if you take the PQth part of the harmonic representative of here, that will also be harmonic. That's where the Kähler condition is used, if these words make sense. So using this Hodge theorem business, you can prove a global version of the del-del-bar lemma. Recall what's the del-bar lemma locally? We say that if omega is a closed real 1-1 form, it's square root of -1 del-del-bar phi for some phi, right? So for a global version, suppose you have a compact Kähler manifold. If omega is a declosed 1-1 form, then it is D-exact if and only if it is del-del-bar exact. What this means is if you have a declosed 1-1 form on a compact Kähler manifold, then omega is d-eta, where eta is a 1 form, if and only if omega is del-del-bar phi for some function phi. In particular, I mean, moreover, if omega is a real form, then omega is del-del-bar phi for a real valued function phi. Okay, so this is a global version of the previous local lemma that I stated. Okay. So if omega is a Kähler form, then it defines a de Rham cohomology class omega, meaning that if omega is a Kähler form, what does this mean? It means that omega is a closed 1-1 form such that, actually might as well just write it once. So what does it mean? Omega is a Kähler form if omega is a 1-1 form, firstly. Secondly, omega is real, that is omega equals omega bar. Thirdly, d omega is 0. And lastly, omega is hij bar dzi wedge dzj bar sum over I and j, where hij bar is a positive definite matrix. Okay, so that's a Kähler form. Alternatively, omega of xy is gjxy, where G is a compatible Riemannian metric whose Levi-Civita connection coincides with the Chern connection of this. Okay. Now, if you give me a Kähler form, in particular, it's a closed 2 form. So it defines a de Rham cohomology class. And this de Rham cohomology class is never 0. The reason is, if you take omega raised to n by n factorial and you integrate it over m, I mean, if you choose any representative of this, you get the same answer thanks to Stokes's theorem. This is due to Stokes. And the point is, this is the integral of the volume form of the corresponding Riemannian metric, which is always strictly positive. Yeah. So in other words, omega is never equal to 0 for a Kähler manifold. Okay. So what does that mean? It means in particular that, sorry if you're getting seasick because of all this change. The point is, in particular, if M is a Kähler manifold, then what happens is that omega, which is a 1-1 form, is not the 0 class, right? Now the point is, because of this, H2 is H11 direct sum H20 plus H02. So in other words, H2 is not 0 for a Kähler manifold. But if you take the Hopf surface, so for example, if you take the Hopf surface, Z2 raised to nz, this is diffeomorphic to S1 cross S3, and the H2 of S1 cross S3 turns out to be trivial. Therefore, this can never admit a Kähler metric. Okay? So there's a very quick proof that the Hopf surface can never admit a Kähler metric. Anyway, coming back to this, every Kähler form in this cohomology class is of a very specific type. It's omega plus square root of -1 del bar phi for some smooth function phi. Why is that so? Because every Kähler form in this, it differs from omega by an exact form, and everything that's exact is del bar exact thanks to the global del bar lemma. Okay. Right. So let's look at some examples of Kähler manifolds. So firstly, if you do produce an example of a Kähler manifold, any submanifold of it, and whenever I say submanifold, I always mean embedded submanifold. Any submanifold of a Kähler manifold is Kähler. Okay. You can simply restrict the metric and it'll continue to be Kähler. So so we've already seen that the complex torus with the Euclidean metric is an obvious example of a Kähler manifold. Somewhat more non-trivially, and this is extremely important, CPN, which recall is simply as a set, it's a set of all complex one-dimensional vector spaces through the origin in Cn+1. So this manifold has a nice Kähler metric, which is called the Fubini-Studi metric. And its formula locally is as follows. So recall that in the Fubini, if you take CPN, the coordinate charts of CPN are obtained by setting one of these functions, one of these homogeneous coordinates to a non-zero thing. That is, if you take this open set and you define the coordinate charts as Z1 is X1 by X, might as well just write this down instead of. So recall that if you take CPN, it is a quotient of Cn+1 minus the origin by this. So if I take X, right, and if I take this particular space, this open set, then Z1 is X1 by X0, Z2 is X2 by X0, etc. So in these coordinates, coming back here, in these coordinates, the Fubini-Studi metric is given by this explicit formula. So you take log of 1 plus mod Z square and take del bar of it. That gives you a 1-1 form. And you can verify that this 1-1 form is indeed a Kähler form. In other words, if you actually write this down, if you write the local formula for it, you will get a positive definite matrix. So this is Hij dzi wedge dzj bar, where Hij is a positive definite quantity. And I'll leave this to you as a nice exercise to actually calculate this matrix and see that it is positive definite. Now, of course, this is only valid in this particular chart. What about in the other charts? Well, you can simply take the coordinates in the other charts and simply write the same expression, 1 plus mod square, sum of mod squares of the coordinates of the other charts. Okay, the same expression will work. And I'll leave that also to you as an exercise to check, right? So by the way, how did anyone come up with this metric? I mean, this seems like a very random construction, but it is not. I mean, the last time I mumbled a few words about Chern classes, if you remember them, if you take the O1 line bundle, it has an obvious metric, and the Chern connection associated to that metric, its curvature is precisely this form. Okay. Its first Chern form up to a factor of 2 pi is basically precisely this form. Okay, so that's how you come up with this, if you didn't know it already. So as a consequence, since CPN has a Kähler metric, if you take any sub-variety, if you take any sub-manifold of CPN, it is Kähler, because you can simply restrict the Kähler metric to the sub-manifold. Okay. But as I said earlier, if you take a randomly chosen torus, it is of course Kähler because you have the Euclidean metric on it. But unfortunately, it will not be projective. It will not satisfy the criteria required for the Codera embedding theorem. And why does it not satisfy the criteria required for it is a longer story. Again, it's there in Griffiths and Harris's book. The key words are Riemann bilinear relations, if you want to look it up. Okay. All right. So equipped with all these definitions, we are at least at a point to state the Calabi conjecture or a Calabi conjecture. There are several conjectures that Calabi made, of which we will state all of them. Just a moment. Let me just see if I have enough charge. Okay, I do. Sorry about that. So, all right. So one of Calabi's many conjectures is as follows. And I like calling this the volume conjecture. I mean, this term was used by Shushong Chen, so I don't know if it's standard. So Calabi's volume conjecture is as follows. Given a Kähler class, omega, so you're given a de Rham cohomology class that admits at least one Kähler metric, okay? And you're given a volume form, an NN form, which is positive. What does that mean? Again, let's go here. So eta is locally some function f times dz1 wedge dz1 bar wedge dz2 wedge dz2 bar, etc., where f is strictly positive. Okay, so eta is a volume form. A volume form, if you wish. Okay, so it's a positive top form. Right. So given a Kähler class and a positive form, there exists a unique Kähler metric in this class, so that this given form is genuinely the volume form of this particular Kähler metric. In other words, the data you're given is a positive form, top form, and a Kähler class, meaning a de Rham cohomology class that contains a Kähler form. And what you need to produce is another Kähler form in the same cohomology class, whose volume form is the given form. Okay. So notice that this is a PDE. It may not appear to be a PDE, but it's actually a PDE. Why is it a PDE? Because every Kähler metric in this cohomology class is of a very specific form. It is of this type, omega plus square root of -1 del del bar phi, thanks to the del del bar lemma. Okay, so every Kähler metric of the type we are looking for is of this form, and what we want is a smooth function phi that satisfies this equation. Omega sub phi raised to n is eta. So omega plus square root of minus 1 del bar phi, which depends on two derivatives of phi, this raised to n is given. Okay. So this equation, if we were to write, I mean, let's actually explore this equation a little bit further. So omega phi raised to n is this, right? So locally, near a point, omega is del bar exact psi by the local del bar lemma. Okay. So in other words, locally, this b is the square root of minus 1 del bar psi plus phi raised to n. What is this? This is the determinant of this matrix. Del zi del z bar j times I dz1 wedge dz1 bar wedge I dz2 wedge dz2 bar, etc. Okay. So basically this expression here is the determinant of the complex Hessian times this thing, but basically it's just the determinant of the complex Hessian. In other words, what the Calabi volume conjecture is saying locally is you want to find a function the determinant of whose complex Hessian is a given function locally. This is what it's saying. Okay. So this is a highly nonlinear equation because you are asking me to find a function, take two derivatives of it and take the determinant of it, the Jacobian, right? So that's a highly nonlinear function and you are prescribing this nonlinear function for me. Okay. So it's a rather complicated equation. It's an example of a complex Monge-Ampere equation. The words Monge-Ampere, Monge and Ampere studied these kinds of equations, determinant of the Hessian of a function being given. They arose from a very, very different context for them, from applied mathematics called optimal transport. They studied real Monge-Ampere equations. These are complex Monge-Ampere ones. Nonetheless, I hope I've convinced you that this is a rather complicated partial differential equation, this particular question. The second thing here to note is if you find such a function phi satisfying this, then you would have solved only a part of this conjecture. You would have answered existence, not uniqueness. Uniqueness says that there's only one such omega prime. In other words, if you have two such functions, phi and c satisfying this equation, the omega phi and omega c should must be the same. In other words, del bar of phi must be equal to del bar of c. Let me actually write this down. What does uniqueness entail? It means that del bar phi equals del bar c. That is del bar of phi minus c is 0. But this implies phi minus c is a constant. Why does this imply there's a constant? The fastest way to see this is to multiply by phi minus c and by omega raised to n minus 1 and integrate this. Use Stokes' theorem to transfer one derivative to this one, right? This is always negative. Strictly, this is negative and it's equal to 0 if and only if del of phi minus c is 0. Okay, this is like the gradient square of phi minus. Okay. Nonetheless, so in other words, this question is equivalent to saying, find a smooth function and prove it is unique up to a constant so that this happens. Okay. So Calabi's volume conjecture is this complex Monge-Ampere equation. This particular Calabi conjecture was solved by Yau, I think in the late 70s or early 80s, I don't remember when, in the affirmative. So by now, far more general PDE results have been proven. Okay, so there are various ways to generalize this particular PDE. Many people have worked on it, including myself, and several results have been proven. Okay, so here's one more example of a conjecture of Calabi, Calabi's Ricci conjecture. So recall your Riemannian geometry, recall the Ricci tensor. So this is a measure of the curvature. So if you take a Riemannian metric and take the Levi-Civita connection, right, then you have the Riemann curvature tensor. And if you take a trace of the Riemann curvature tensor, you get the Ricci tensor. Now, this tensor is of the same type as the metric tensor. In other words, the metric tensor is locally some linear combination of dx tensor dy, right, roughly speaking, for a surface. The Ricci tensor is also roughly something tensor, something else. It's a 2 tensor. Yeah. Now, just like you can form a 2 form out of the metric tensor if you give me a metric that is compatible with a complex structure J, you can form a 2 form omega out of it. How do you form it? Omega of x comma y is g of jx comma y. Just like that, you can form a 2 form out of the Ricci tensor of, let's say, a Kähler metric. And the 2 form is Ricci of jx comma y. It's a 2 form, as you can verify. In fact, it's a 1-1 form. And this 1-1 form is of a very special type. This 1-1 form is actually closed. Okay. And its cohomology class is something that we recognize very well. It's up to a factor, the first Chern class of the manifold. Okay. So this 2 form is called the Ricci form. So Calabi's Ricci conjecture is as follows. If you give me any representative of this cohomology class and give me a Kähler class, find a Kähler metric in this Kähler class so that its Ricci form is this given representative. In other words, you're giving me a representative lying in a certain cohomology class, and you're asking me to find a Kähler metric whose Ricci form is the given representative. Even more simply, it's basically asking you to find a metric with prescribed Ricci tensor. Okay. In particular, if the first Chern class of the manifold is 0, then you're asking me to find a metric whose Ricci curvature is 0. That is, it's Ricci flat. Okay. So in particular, if the first Chern class is 0, then find a Ricci flat Kähler metric. Okay. So why is that an important question? Well, what is a Calabi-Yau manifold? Well, different people define these things differently. But for me, a Calabi-Yau manifold is a compact complex manifold that has a Ricci flat Kähler metric. So the Calabi's Ricci conjecture, if it is not a conjecture and if it's a theorem, if it can be solved, tells you that if you can calculate the first Chern class of a manifold and see that it is 0, it is automatically a Calabi-Yau manifold. Yeah. So this question, that is Ricci of omega equals eta, this question can be reduced using the del bar lemma to the previous conjecture of Calabi that Yau solved. Okay. To the volume conjecture, and hence can be solved. Okay. How do you reduce that? I'll see if I have time after I finish these 2 slides to tell you that. So the bottom line is, if the first Chern class is 0, the manifold is a Calabi-Yau manifold. Okay, so these are the so-called Calabi-Yau manifolds. And here's a concrete example of a Calabi-Yau manifold. So consider CP4, yeah, and in CP4, so what is CP4? CP4 is a quotient of C5 minus the origin, quotiented out by this. Okay, so in C5 you have these coordinates x1 to x4, right? Recall that I told you an algorithm to come up with submanifolds of CPN. You take your favorite homogeneous polynomial. In this case, what is this polynomial? It's x0 raised to 5 plus x1 raised to 5 plus so on x4 raised to 5 and set it to 0. This is a subset of C5, right? Now, this subset gives you a well-defined subset of CP4, and it turns out it is a submanifold. And remember, we stated a theorem that guarantees that this will be a submanifold if you call this function as f, if the gradient of f is not 0 on C5 minus the origin, right? And what's the gradient of this? It's simply 5x0 raised to 4, 5x1 raised to 4, and so on. And this is not 0 on C5 minus the origin. So whatever this beast is, this is a genuine compact complex submanifold of CP4. Okay. I claim that this manifold has first Chern class equal to 0. And why does it have first Chern class equal to 0? For that, I need to give you a formula that enables you to calculate this Ricci form. Okay. So the formula is as follows. Unfortunately, I don't have time to prove it. So the Ricci form of a Kähler metric is given by this formula. It's square root of -1 del bar del log of the determinant of Hij bar. Okay, a very pleasant formula. If you remember your formulae of Riemannian geometry, the Ricci tensor has a very obnoxious and painful expression. Thankfully, in Kähler geometry, it's very straightforward. It's del bar locally, it's del bar del of something. Okay. Recall that this is nothing but omega raised to n by n factorial expressed locally. Okay, so, or rather, omega raised to n is determinant of Hij bar times I dz1 wedge dz1 bar wedge so on. Okay, if I divide it by n factorial, you get this. Okay, so this is a rather pleasant formula that we have in Kähler geometry for the Ricci tensor, Ricci form rather. Now here is a calculation, and this calculation is not trivial. This calculation can be found in various sources. For example, it's in a paper of Liu in the transactions where she needed it in some context. For the Fubini-Study metric, notice that CP4 already has a nice Kähler metric, the Fubini-Study metric. You can restrict it to this beast, the so-called Fermat quintic, to get a Kähler metric. You would naively hope that that Kähler metric is Ricci flat, that Kähler metric is Calabi-Yau, but it is not, unfortunately. Nonetheless, the first Chern form of this with the Fubini-Study metric turns out to be del bar exact. Okay, it turns out to have this explicit formula. And this I'll leave to you as an exercise, or you can look it up in the paper I just referred to. Therefore, explicitly, we see that the first Chern class is 0. And since the first Chern class is 0, Yau's theorem tells us that there is a unique Kähler metric in any Kähler class whose Ricci curvature is 0. Okay. Of course, you might wonder, if you're a physicist, you might wonder, can you approximately find a formula for that Kähler metric? Can you approximately write an expression? Can you calculate it approximately? You can do it on a computer. Unfortunately, there's no direct formula for it. And the algorithm is also not straightforward. It was proposed by Donaldson, and it was first numerically computed by Michael Douglas. Okay. So in this last slide, I'll just mention other conjectures of Calabi. So firstly, Einstein metrics are those metrics that satisfy the Ricci tensor is a multiple of the metric itself. Why are they called Einstein metrics? Because they're somehow related to general relativity. I can't go into the context right now because I don't have enough time. Now, anyway, the bottom line is under appropriate conditions, Calabi asked whether Kähler-Einstein metrics exist. That is, if you were given a compact Kähler manifold, can you find a Kähler metric which is also Einstein? Okay. So the answer is no, was known to be yes when lambda is 0 and -1. When lambda is 0, it's precisely Calabi-Yau, which was done by Yau. When lambda is -1, this was done by Aubin before Yau, and Yau also gave a proof. Okay. When lambda is positive, when lambda is +1, shockingly enough, the answer is no. And this was done relatively recently, a decade ago. The works of several people, notably Chern, Donaldson-Sun, and Tian, led to a resolution of this Yau-Tian-Donaldson conjecture. Okay, so this conjecture of Calabi was solved only a decade ago, but Calabi also conjectured that constant scalar curvature Kähler metrics exists under appropriate conditions. In other words, Kähler metrics in a given Kähler class whose scalar curvature is a constant. That conjecture is still open. In fact, we don't even know what the correct conjecture is in this case. And he also conjectured something else, but that's a little more complicated. But yeah, so basically Calabi has been guiding this field since a long time. But this result in 2012 was a culmination of many works and solved a major conjecture. In any case, I believe this workshop is largely focused on Calabi-Yau manifold. So this is the relevant slide for the same. Okay, so I'll stop at this point, run out of time.
Thanks, Vamsi. Questions? Okay, there doesn't seem to be any question. Maybe I will ask a question. You can. So for positive lambda, what makes it like the answer no? Can you briefly give a hint or whatever?
So basically, what it turns out, so what goes wrong really is that you get an equation of this type times something, and if you want to prove a priori estimates for phi, you want to use the maximum principle, but this minus is the wrong sign. Okay, so that's the problem. So that only suggests that, okay, maybe the maximum principle doesn't work, maybe something clever would work, right? But you can find counter examples. So for example, if you have lots of symmetries, that is, if you have lots of holomorphic vector fields, then the solvability of this equation implies that a certain invariant called the Futaki invariant must be 0. And you can find examples of manifolds which are very symmetric where the Futaki invariant is not 0. Okay. So there are other algebra geometric obstructions. That's what goes wrong. If you've ever heard of these things called Kasdan-Warner, these are theorems in Riemannian geometry, Kasdan-Warner equations. The obstructions that arise for them are similar in flavor to what goes wrong when lambda is positive. Some algebraic geometry goes wrong, basically.
Right. Okay.
The real analog like the Yamabe conjecture?
So yes, so for instance, the Yamabe problem also for the positive case is problematic, right? For the negative case, it's easier. It's the same philosophy, but not quite the same thing, because the Yamabe problem is not quite related to algebraic geometry. This is far more algebraic than that. But philosophically, yes, you're right.
Any other question? All right, let's thanks the speaker. Thank you very much, Vamsi, for the nice talks.
Sure, thanks.
Thanks to you, Diganta, also for sharing.
Okay. Okay.
Okay, then we will leave it now.
Sure.
Thanks.
Yeah.
Have a
bye-bye.
good night.